Hi everyone, welcome back. So today we will be working on a packed binary. So the challenge that we will be working on is Hollywood. So this challenge took me 2 days to solve. It took me a great amount of hours, to be honest, more than 10 hours to solve it. It's a really interesting challenge. So it's been a hard night, I think, solving that challenge. I remember just the couple 2 days I was just working on that until 4 a.m. Yes, it is a really interesting challenge. So before we start solving, don't forget to follow me on Twitter and don't forget to hit the sub button if you are not a follower. And yes, and turn on the notification bell too. Yeah, so let's not waste too much time. What do we have? So new randomization improves code security and this lock is not attached to any hardware security module. So that means that um, it's either the password that is hard coded or something that is going to be checking the password manually. So yeah, so the this paragraph has nothing to give to us. Okay, so if we start the program, what do we have? So what's the password? And if we send, for example, A, B, C, D, we get the CPU turning off and we see this randomization or this weird code that we are trying to see. It looks like the same challenge as the SLR challenge, but I don't we don't know for the moment what is exactly the implementation or what is exactly the mitigation that is implemented into this code exactly. So the first thing that I've tried to do when interacting with something like that was to I tried the first thing that I tried is I tried to reverse engineer the code statically, but it seems out that there was a lot of jumps that was happening and a lot of weird things, and then there was this little decryptions. So this is just was giving me the was just giving me the taste of a backer. Yes, I remember just working on a backer on some other CTF, but this one just gave me the flavor of a packer. So what I thought of was just as an entry point to analyze this binary was just to figure out, for example, where the password was coming in. So if we reset, so for example, A, B, C, D, E, for example, F, or let's say 41, 41, 41, 41, stuff like that. Well, after running the code, it just came out that the password was at the address I remember, if I remember that correctly, it was 26 something, if I'm not wrong. 26. Let's check this. So 26 is not there. Let's try to refresh the code. See, for example, 41, 41, 41. So if we go and check that one. Yes, so this is exactly where the input goes in. So that means that the code was loaded inside of this address, which is 26. And no matter how much I refresh the page, it's going to be always 26. So this is just a great entry point so that I can try to solve the program off. Another interesting thing I tried to do was I tried to restart the program again and I tried so basically to debug it. So this is what I tried to do. So if we hit the enter, so what is the password? So for example 4141. So as you can see, if we reset again, I tried to step basically inside of the code to see what are the actual, as you can see when you tried for example to execute the jump um, to the actual address plus 4, it is going to be executing some things or some instructions before the next jump, which are these instructions, which is actually overridden by some weird instruction, which is dadd.b. But as you can see, we have instructions that are executing if we step. So I cannot step actually too much because there is a lot of instructions that is going to be actually executed. So the best way to do this was to think of something that can emulate this code or that can emulate this MSP 430 code. So I've searched on the internet and I find out this little emulator that we have, which is an interesting emulator. So basically, what you have to do is just clone the GitHub repo And after doing that, you have to install, I suppose, you have to install this GDB MSP 430 if you want to debug, but I didn't use that. So I basically just installed this two packages in order to be able to just make the files of the emulator. So yes, so after doing that, so we have the files, and we have also, and I also have dumped the program that we have in the Microcorruption website, which is this one. And basically I'm going to be emulating that, trying to understand exactly what are the instructions that was executed. So basically the example that you have guys in front of you is an example of a packer. And for people who do not know what a packer is, so packers are programs that we use, and basically the format of them is, let's say for example you have let's say an example of that could be something like this. So a packer is basically, this is your program, this is your, let's say for example your binary that you have. So this is your binary that has all the instructions inside of it. When you do, for example, create a packer, so a packer is something that is going to be taking all this program and packing it into another binary, which is the one that you have in front of you. And what the packer is going to be doing, so this is your program, this is your, let's say, the result of the packer is going to be another program, which is a packed program. So this is a packed program, which is this one. And in front of the packed program, you will basically see something like a wrapper. So a wrapper is the is another, actually, just let's say functions or programs that is going to be unpacking the program on runtime. So the same thing that is happening in here. So basically this program, if you try to reverse engineer, if you try to reverse engineer it statically like that, you won't know exactly what is happening, because he's doing some decryptions at runtime. As you can see, he's decrypting 1 byte at runtime. So you have to execute that program and debug it on runtime in order to be able to know what are the instructions that was executed. Yes, so this is why we need emulators. This is the point when you need a debugger or an emulator. So in our case, we are basically going to be using an emulator, because we are using basically MSP 430 architecture, and the way to just emulate this is just by using emulators. We cannot emulate something as the, I cannot debug MSP 430 on Intel 8664, so that's why I need an emulator. So this is the emulator that we will be using. And yes, so after installing all of that, so basically we have the emulator in front of us. So the way we can use the emulator is we add, for example, dash t to create a trace file of all the instructions that was executed, and dash x to make them in hexadecimal format. So what I did simply was just executing the emulator. So executing the emulator with the dash t. To me, that means that we are going to be using a trace file. So I'm going to be naming the trace file, for example, trace file. I'm going to be naming that file trace file. I'm going to be adding the dash x to say that I want it in hexadecimal format. And then after doing that, I'm going to be giving the program of the microcorruption that we have, or the binary that we have. So after that, the emulation started, and he's asking what is the password. So the password is going to be, I'm going to be saying, for example, a bunch of A's. And if we try to see, we see that we have a huge amount of instructions that was executed, and we have this trace file. So um, if we try to cat that trace file, we see a lot of hexadecimal instructions that were executed. So I'm gonna be opening up that file inside of Sublime. So trace file. So this is the trace file. So as you can see, now we will be just getting that out of our ways, and let's go back to the trace files. So if you look at the trace file, we have some great amount of instructions that was executed. So for example, I will be using now, we need to disassemble this instructions. So the way to do that, I tried to search for a disassembler for the MSP 430, but at the end I ended up with just using the microcorruption one. So to understand exactly what those instructions were. So to do that, we can just simply now see what are the disassembly, what the CPU was literally trying to execute. So this is what the CPU was executing. Now, in all this code, basically there was a lot of code. I tried to exactly figure out some entry point of that. So, to do that, the first entry point that I have note is that the password will be loaded into 26 0x2600. So I tried to search for that address. So if we search for that, we just have to flip the bytes and we get this instruction. We see that the 26 was in there, and we have two calls. So if I try, for example, to check this block of code, um, we see, for example, we have this one, which is moving. So we are moving that address inside of the stack pointer plus 6, and we see some random data. We see a lot of, well, it's not random data, it's a lot of instructions that was happening, as you can see. Now, what I tried also, so I tried to figure out a pattern out of that code. So I tried also to search for since when we click on continue, we see that um, there are characters who are what's the password. So I tried to also search for the characters what's the password inside of that code, since he will be executing that. So I suppose there is a code that is going to be calling the print command to print the what's the password. So to do that, I just try to use Python to convert, for example, ord of, for example, W, which is 78. We want them in hex since I'm going to be searching in hex. So it's going to be 57, and the A we know that it is the H is going to be, for example, um, the age is going to be, for example, 68 and so on. So I try to search them. For example, for the 57, if we try to search for the 57, so 57, 57, 00. For example, I got this one, which is this instruction. If we try to see the block with these instructions, we figure out that we have this one. So we are basically moving 57 inside of the stack pointer, and we see the same pattern of code. It is moving the register 12, as you can see, the same pattern. It's moving a random address that I don't know yet what it's doing to the register 12 and so on, and then it's branching to the register 13. So this is just a simple behavior that packers do, simply to obfuscate the code. They basically try to execute instructions and then branch to other codes so that you cannot reverse engineer directly statically. So yes, so this is what was happening, and the same pattern happened also with the other character, which is the H, for example. The 86, which is this one. If I try to disassemble this one, we see, as we can see, the same pattern. So he's moving something to the stack pointer, then he's doing all this code that does not make any sense. And then there is this interesting call, which means that doing all this is just to print a character inside of the screen that we have, or back to the screen, or back to the output, or whatever. And the same also pattern repeated with the other ones. So this was now some kind of pattern is repeating. So whenever he want to do an instruction, so he basically tried to do that. Another thing that I have spotted that was really interesting too is that he kept on using the register 14 to do those weird instructions, and he kept on using also the register 13 to branch and register 12. Um, but I didn't see any call, for example, to register 9, register 8, register 7, register 5, register 4, etc. So this is just came to the conclusion that I think he will be using the other registers for other things. So what I've tried to do also, back to the 26 address that the password will be loaded at. If we take a look back at this, if we disassemble that, So there was two little instructions that were really interesting to look at, which are this one and the other one, which is this one. So if we try to check the second one, we basically get moving that address inside the register 5. So that means that he will be using the register 5 as the beginning of the password. So there is a password check that is going to be happening. And as we can see, this address, the instruction of the the address of the second instruction that the move 26 to register 5 is happening is under the above one. So that means that after just doing the password thing, just printing the what's the password message, he will be loading the 26 into the register 5. So after a long time of let's say reverse engineering all this code, I just came out with those instructions, and as you can see, by the way, the same pattern was repeating. So I was trying to step little by little inside of the code after I disassemble all of it, and then I just try to delete all this trash code since it does not make any sense for me. It's not going to be the instruction that I want. This is the instruction that we want, and all this is some kind of trash code. So I try to step little by little inside of all that code that it was generated until I finally, just after 2 hours of stepping into that code, just to extract the interesting code that was truly executed, which is this one. So this was just to print the what's the password, and after that we see a call just to basically read what is in the input into this address. And after that, he was basically moving the address, actually um, the address of the first character inside of the register 5, which is the 0x26 00, and after that he clears the register 6 and adding what's at the position at that actual character, which is register 5. He adds actually what's in the register 4 with that one, and basically register 4 is equal to that one, which is register 4 plus the what's actually the character, or what are actually the word that is in the register 5, since the register 5 is having a 16-bit value, which is basically two words. Yeah, or is it actually one word? Yeah, it's actually one word, not two words, because one word is 2 bytes and register 5 is having 2 bytes. So yeah, so after that we do a swap. So we swap the bytes of the register 4, and after that we actually just associate a value. So we affect the value that is in the register 5, and then we do a plus. So basically we are affecting the value that is in the register 6, that is in the register 5 to the register 6, and then we increment the value of the register 5. That means that we are going to be checking the second one, which is which is actually the second character. Yeah. um, this is exactly what is happening. So yes, we will be incrementing that. So yes, so that one register 5 plus plus, and then we will be XORing what's in the register 6 with the register 4. So register 6 equals to register 6 XOR register 4, and then register 4 equals to register 4 XORed with the register 6, and register 6 is going to be equal to register 4 XORed with a register 4. So basically those three instructions implements an operation that we knew variable, which is the instruction or the operation of swapping. So we are basically swapping the values of register 4 and register 6, and we can check that out if we want. For example, taking 1 and 2. So for example, x equal to 1 and y equal to 2. So if you take, for example, x equals to x XORed with XORed exactly with y, and then you do, for example, y equals to x XOR y, or y XOR x. It's going to be y XOR, basically now the x is having x XOR y, so it's going to be x XOR y. So the y and the y XOR themselves becomes a 0. It gives you x XORed with a 0, which gives you x. And now if you came to the last instruction, which is the last XOR, so y is going to be x XOR, or x is going to be x XORed with y, which means that it's going to be x XOR y, which is this one, and we XOR it with another x, since the y is now equal to x, which gives you basically y. So now that means that this block of data is just going to be swapping the values of the register 4 and the register 6. After that, we cleave the register 7, and then we compare what's in the register 4 with this value, and then we set the result of the compare. We move the result of the compare, which is going to be in the statute register inside of the register 7. And after that, we clear the register 4, and then we do another conversion with the result that is going to be in the register 6. We compare it with this value, and then we end the statute register with the register 7, and then we basically just clear again the register 6 and do some rotations inside of the register 7, etc. So it comes out to be that these two values should be equal in order to open up the door. These two these two values should be equal. So this is the interesting thing now. The interesting thing is that the first thing that I tried to do is I tried to mimic exactly the code. So by mimicking the code, I wanted to, for example, just by trying to mimic the code, I tried to go, for example, for all the words that we have. For example, for in the range, well, this is how I try to solve exactly. So I try to go inside all of the words that we have, um, all the words that we have. So I tried to do a simple brute force to do that. So we started from the 0x00 1 back to the 0xFFF. Since the register basically 5, since the register 4 basically is a 2 bytes, so it's going to be E1 words. So yes, so I tried to do all of them, trying to break up to find or figure out exactly what are the register 4 and the register 6. And by doing that, so by just incrementing with a 1, obviously, so the word, the temporary word I'm going to be choosing um, is basically just the swap of bytes. For example, I'm gonna be just swapping bytes, obviously, swapping bytes of the word that we have, XORed with exactly the 0xFEB1, which is this one, FEB1. And if that actually temporary plus a word, if we try to end them with the 0xFFF to make sure that there is in the range is equal to actually this value, but we have to swap them since we are actually um, the first thing that we did was adding, and then we did a swap. So basically, if we try to figure out exactly what are the two values that we have in the register 4 and the register 6, we have to reverse back the operation, and by doing so, we have to swap also the bytes in here that we have. And we gotta make sure that this is equal to the 0x9298. So the 0x, so 98, 92, 98. Um, to do that, we can simply also, instead of doing the swap bytes, we can swap just these two bytes. So to do that, so you can just directly um, swap these two bytes directly without having to swap the result that we have. So if so, we just print the answer. We print just the two words that we have. Print the two words that we have, and then we break. This was the first attempt that I did, and basically this attempt was simply just by looking at the code, but it seems out to be that this was not the password. I tried that with several passwords that was generated using this code, but somehow it does not work. So I thought the next thing that I would do is just simply by adding another byte. So basically, if I send, so what was happening exactly, guys, just so that you can understand. So if the password, for example, is equal to AABBCC. So what I tried was just using this 4 bytes, since I was sending 4 characters, and 4 characters are equals to 2 words exactly. So this is one word and this is another word. So a word is a 2 bytes data. So it came out that was not accepted by the password. So it was kind of he was kind of checking the length if it is equal to 4 or above 4. But I somehow, by adding another byte, um, somehow the door just opened and unlocked for me. So by adding this CC to our code that we have, we can just directly now open up just another brute forcing with another variable just to figure out exactly just to figure out exactly what is the third word. And the interesting thing is that there was also a relation between the word 1 and the word 2 that we have in front of us. So the word 3 should be having a relation with the word 2. So now we can simply directly just um, create a simple program that is going to be just solving this little equations that we have. And by the way, you can also use Z3 to solve this equation. But I'm gonna be just going with the traditional brute force that I'm going to be implementing myself. So the first thing that we have to do was just to simply go, for example, to find out or figure out exactly what is the word one. So the word one is going to be in the range of the um, 0x001 obviously, and we will be going on to the FFF, and we will be incrementing with a 1. And then we start with the second word. That's going to be the same thing as the other one. So, and we'll be incrementing with a 1. And now we start setting up the registers that we have. So register 4 should be equal to the word 1 that we will be trying to test. So basically, the register 4 should be having a value of the password, a word of the password, and the register 6 is going to be. So he's basically checking with two words each time, which means he will be checking 4 characters at one time. So register 6, I will be initializing it since it was initialized with a 6, but after doing the operations, we can see that register 6 would be, I will be trying to just brute force with e word 2. That's why I did 2 loops. Now, after doing that, we start doing the operations that he was doing. So register 4 plus the word 2 that we will be trying, which is containing in the register 6. um, and then we will be just making sure that it is in the range of 16 bits. So I'm gonna be just ending that with 0xFFFFF. And then register 4 is going to be swapped, so I'm gonna be swapping that one. So swap bytes of register 4, and I need to define this operation. So I need to define this operation. So swap bytes. So it's going to be getting a value. So I'm gonna be returning. So how do we do the swap? So to swap, for example, 0x1, 2, 3, 4. So if we try to just set that in binary, so it's actually like that. So if we just set that, for example, to a 1, so it is 0, 0, 0, 1. 0010, etc. So this is the binary equivalent of this one. So this is the binary equivalent of the number that we have. So the next thing that we have to do, so in order to implement this one, so basically this one thing, um, 0 0 1 0 0, yeah. So one thing to do now is to basically do this web byte. So basically we want these bytes to become in here. So to do that, so well, we want those ones, for example, to become in here, and then we want those ones to become in here. So we basically want to extract those bytes, those first 8 bits. So to do that, so we need to do value, and we end them with 0xff0. By doing that, so we extracted those ones. So just assuming that this is equal to the value, and this is equal to the value. After doing that, so we just shift them with 8, and then we basically do just a simple OR with the other ones, which is value modulus 0x00ff, and then we simply just shift that to the left. So we basically so we end this as an AND. So basically after doing that, we extract those values and then we shift them to the left with 8 bits. So like that we will be just doing this web bytes. So this is an AND. So we end it with 0xff0, and then we end it with 0x, and yeah, so it should be good. So after doing that, so after swapping the bytes, the next thing that we have to do is we have to take a look in here. So after swapping the bytes, we have, so register 6 should be equal to the, so should be XORed with the register with the word 2, and after that we just have to swap the contents of the register 6 and the register 4. So yeah, so let me check that out. So we are so I have just pre-computed the values of the register 6 and the register 4, and then we have to just add, so we end that with 0xFFF to make sure that it is in the range, since it is an addition operation. And yeah, so after doing that, so we are going to be then just setting the word 3, which is going to be the register 6 XORed with the 0xFE B1 B1, yeah, B1. And after that we check if the so if the resistor for or the word 3 that we have just pre-computed, which is this one, that we have just going to be checking if it is the one or not, is equal, we end that obviously with we have to end that with 0xFFF, make sure that is in the range since it is an addition operation, and then we check if it is equal to 0x. We obviously just swap those bytes, since we will be just obviously, instead of applying this swap bytes on this operation, we will be just swapping it here, which is 98 92. And after doing that, so then this is just the solution that we should be printing. So solution is, and we start just writing 3 values, 3 bytes of data. So 2.4x, 2.4x, and 2.4x, and then we just set so we swap the bytes of the word 1 and to the word 3. Yeah, so if we try this out, so it's going to be well, I forgot about, we have a format that we have to check, which is format yeah. So yeah, so those are the passwords that we have generated that can open up the door just ranked by brute forcing those equations. So we can try this one, for example. If we try that, and yes, so the door is unlocked. So this is basically how I try to brute force this little program that we have in front of us. So it's basically a simple check. Another interesting solution might be to use Z3, but I just go with the traditional way. You can use also Z3 to brute force the equations. So basically the equations that we have are these ones, and then the conditions are basically just the equality. So it should be equal, register 6 should be equal to 0x fb1, and register 4 should be equal to this value, which is in here, which is 92, 98. So those are the two values that are in there, and yes, I hope you have learned something out of that. Actually, it took me 2 days. I was literally, the hardest part was just to get actually the code that the processor was truly executing, not the code of the packer. And yes, I was literally going into the trace file, trying to trace all the instructions that was there. I think there is another solution that might be more good than this. And I think if you can just write a simple I know another emulator that can just emulate directly and get the instruction that was executed directly, that would be better without just the code of the packer. Yes, if you have tried to solve the challenge with another way, don't forget just to write me how you solved that in the comments. And yes, so let's share knowledge together. So I think we had the end of the video. Don't forget to follow me on Twitter. Don't forget to hit the sub button too. And yes, we still have one solution, or um, one simple challenge to solve, which is Chernobyl. I think I didn't solve that on the server. We gotta solve that on the server too. Yes, so we still have one challenge, which is Chernobyl to be solving, and I think the next video will be the ending. So yeah, so have a nice day and bye.